Hello and welcome. Tonight we'll be exploring one of the greatest scientific revolutions in human history. It is a story that unfolds not through sudden explosions of discovery, but through decades of quiet observations, patient measurements, and the willingness to question ideas that once seemed beyond doubt. As you settle into a comfortable place, you may find it remarkable that the universe above your head has not changed very much over the past 50 years. The stars still rise. The Milky Way still stretches across dark skies. Yet our understanding of what those lights truly represent has been transformed almost beyond recognition. So allow your thoughts to drift gently upward, toward the night sky, and let us begin. If you had stood beneath a clear sky sometime in the late 1970s, you would have seen a universe that felt both familiar and reassuring. Astronomers had already learned an incredible amount. They knew the planets of our own solar system. They understood that our Sun was one ordinary star among hundreds of billions inside the Milky Way. They had begun to accept that the universe itself was expanding after a tremendous beginning often called the Big Bang. It seemed as though humanity had assembled most of the important pieces of the cosmic puzzle. Of course, there were still unanswered questions. Science always leaves room for curiosity. But few people imagined that some of the biggest discoveries were still waiting quietly in the darkness, hidden just beyond the reach of the instruments available at the time. Then, in the autumn of 1977, a remarkable journey began. A spacecraft named Voyager 1 lifted away from Earth, carrying with it humanity's hopes of exploring the outer solar system. Engineers expected it to visit Jupiter and Saturn before continuing into deep space. No one could have guessed that the little spacecraft would eventually become a symbol of an entire era of scientific discovery. As Voyager travelled farther from home, something equally extraordinary was happening back on Earth. Our telescopes were improving, our computers were becoming more powerful, new generations of scientists were beginning to ask questions that earlier generations could barely imagine investigating. It was almost as if Voyager were carrying humanity's curiosity outward, while, at the same time, our understanding expanded inward, revealing hidden layers of reality that had been there all along. One by one, old assumptions quietly disappeared. For thousands of years, people wondered whether planets existed around other stars. It was an ancient question, but no one had a proof. Then, during the final years of the 20th century and the beginning of the 21st, the discoveries began to arrive. One planet became 10, 10 became hundreds, hundreds became thousands. Today, astronomers know that planets are astonishingly common throughout our galaxy. In fact, there may be more planets than there are stars. Every point of light above you tonight could easily have its own family of worlds, each with mountains, oceans, frozen landscapes, or skies unlike anything we have ever imagined. The universe suddenly felt much larger, but also strangely more familiar. Our own solar system was no longer a rare exception. It was simply one quiet neighbourhood among countless others. Then came another surprise, when the Hubble Space Telescope pointed toward what appeared to be an almost empty patch of darkness. Many expected to see very little. After all, there were almost no bright stars visible in that tiny corner of the sky. Instead, the images revealed something breathtaking. Almost every tiny point of light turned out to be an entire galaxy. Not a single star, not a small cloud, an entire galaxy, each containing hundreds of billions of stars. It was like looking through a keyhole into a vast library and realizing that every book opened into another library beyond it. Scientists gradually came to understand that the observable universe may contain trillions of galaxies. The night sky had not become more crowded. Only our awareness had expanded. Around the same time, astronomers were uncovering another astonishing truth much closer to home. At the very heart of our own Milky Way, stars were racing around an object so massive and so compact that no ordinary explanation could account for it. By carefully watching these stars over many years, researchers discovered convincing evidence for a supermassive black hole resting quietly at the centre of our galaxy. Once again, the universe had become stranger. Black holes were no longer rare mathematical curiosities discussed only by theoretical physicists. They appeared to be common features of galaxies across the cosmos. And yet, remarkable as these discoveries were, they would soon be overshadowed by something even more profound. Astronomers slowly realised that nearly everything they could see, the stars, the planets, the glowing clouds of gas, even every living creature on Earth, might represent only a tiny fraction of what truly exists. Imagine walking into a magnificent cathedral at night, carrying only a small candle. The warm circle of light reveals beautiful stone floors, carved pillars, and colourful windows nearby. Everything beyond that small circle remains hidden in darkness. It would be easy to believe that the illuminated portion is the whole building. Only after sunrise would you discover enormous halls, towering ceilings, quiet corners, and hidden passageways stretching far beyond what your candle could reveal. Modern cosmology has experienced something very similar. For centuries, humanity studied the small portion of the universe that shines. Then, within just a few decades, we began to realize that the invisible parts might be vastly larger than everything we can see. That realization changed almost every branch of astronomy. Questions became more important than answers. Every new telescope uncovered another mystery. Every improvement in measurement revealed another puzzle waiting patiently beneath the surface. Rather than reaching the end of our journey, we had only just stepped through the doorway. Somewhere in the darkness, invisible structures were shaping entire galaxies. Another unseen influence appeared to be gently stretching the universe itself. Ideas that once sounded impossible slowly became accepted parts of modern science, while familiar certainties quietly faded away. It is a humbling thought. The universe above us had remained almost exactly the same. The greatest transformation had taken place within our own understanding. And as humanity learned to see farther than ever before, the cosmos responded with an almost playful reminder that every answer could become the beginning of an even deeper question. As humanity's picture of the universe grew larger, astronomers found themselves asking an increasingly simple question. If we could now see farther than ever before, were we truly seeing everything that was out there? It sounded almost too obvious to matter. After all, telescopes were designed to collect light, and the brighter an object was, the easier it became to study. For generations, light had been our faithful guide, revealing stars, galaxies, and glowing clouds scattered across the cosmos. But sometimes, the most important discoveries begin when something refuses to behave the way it should. In the 1960s, an astronomer named Vera Rubin devoted herself to carefully observing galaxies. Unlike dramatic discoveries that arrive in a single unforgettable moment, her work demanded extraordinary patience. Night after night she gathered measurements, comparing tiny changes in the light arriving from distant stars. There were no spectacular explosions to witness, no sudden flashes across the sky. Instead, there were long hours beneath the stars, quietly collecting clues. Vera Rubin believed that nature often whispered before it shouted. Her journey was not always an easy one. At a time when astronomy was still largely dominated by men, opportunities for women were limited. Some observatories had only recently begun welcoming female astronomers. Yet Rubin never allowed those obstacles to define her path. She remained focused on the questions that fascinated her most, trusting that careful observation would eventually reveal the truth. She also worked alongside an exceptionally talented instrument designer named Kent Ford. Together, they used a highly sensitive spectrograph capable of detecting the faint light from stars far beyond the bright centres of galaxies. That improvement in technology would prove just as important as the observations themselves. Sometimes a discovery depends not only on asking the right question, but also on building the right tool. To understand what Rubin expected to find, imagine children riding a merry-go-round in a quiet park. The horses near the centre travel in a small circle, while the horses near the edge move along a much larger path. Yet they complete each rotation together because the entire platform turns as one. Now imagine a different scene. Picture planets orbiting the Sun. Mercury races around quickly because it is close to the Sun's powerful gravity. Neptune, much farther away, moves much more slowly. This gentle decrease in speed with distance is exactly what astronomers expected to see inside galaxies. They believed that most of a galaxy's mass was concentrated in its bright central region, where countless stars gathered together. If that were true, then stars near the outer edges should orbit more slowly, much like the distant planets in our own solar system. It was a reasonable expectation. Nature, however, had something else in mind. As Rubin and her colleagues measured the motions of stars across the Andromeda galaxy, they noticed something astonishing. The stars far from the centre were not slowing down. They continued moving at surprisingly high speeds, almost as though some invisible hand were holding the entire galaxy together. At first, the result seemed difficult to believe. Scientists are naturally cautious. Extraordinary claims require extraordinary evidence. So Rubin continued observing more galaxies. Again, the same pattern appeared. Then another galaxy, and another. Soon it became clear that this was not an unusual exception. It was happening almost everywhere astronomers looked. Imagine watching autumn leaves circling around a hidden whirlpool beneath the surface of a quiet pond. Even if you cannot see the water beneath, the graceful motion of the leaves tells you that something powerful is quietly guiding them. The stars were behaving in much the same way. Although astronomers could not see the source, they could clearly observe its influence. The galaxies appeared to contain far more mass than all their visible stars, gas and dust could explain. There had to be something else, something invisible. This mysterious substance became known as dark matter. The name itself can sound dramatic, but in truth, it simply describes our uncertainty. It does not mean the matter is black or shadowy in the ordinary sense. It simply does not shine, reflect, or absorb a light in ways our telescopes can easily detect. In other words, it is hidden from our eyes, but not from gravity. Gravity became the messenger. Although dark matter remained invisible, its gravitational pull quietly revealed its presence. Like footprints across fresh snow, its effects could be followed even when the traveller remained unseen. Interestingly, Vera Rubin was not the first scientist to suspect such hidden matter. Decades earlier, another astronomer named Fritz Zwicky had noticed that entire clusters of galaxies also seemed to contain far more mass than anyone could see. His idea was bold, but the evidence available at the time was limited, and many scientists remained unconvinced. Rubin's careful observations changed everything. Her measurements were so consistent, and they appeared in so many galaxies, that the scientific community gradually accepted an extraordinary conclusion. Most of the matter in the universe was not visible at all. This realization transformed cosmology. It was no longer enough to study only the stars that filled photographs of the night sky. Astronomers now had to consider an invisible companion stretching far beyond the glowing disks of galaxies. Surrounding each galaxy appeared to be an enormous halo of unseen matter, extending much farther than anyone had imagined. You might picture a great old tree standing in a peaceful meadow. At first glance, the trunk and branches seem to define the tree itself, yet beneath the ground lies an even larger network of roots, quietly supporting everything above. Those roots remain hidden, but without them the tree could never stand. Dark matter appears to play a remarkably similar role across the universe. The glowing stars are like the branches catching the sunlight. The invisible matter is like the roots, silently holding entire galaxies together. This discovery also carried a quiet philosophical lesson. For centuries, humanity trusted that seeing was the same as understanding. Yet the universe gently reminded us that reality is often much richer than appearances alone. Sometimes the things that shape the world most profoundly are the very things we cannot see directly. As astronomers accepted the existence of this invisible cosmic foundation, a new question naturally emerged. If hidden matter was holding galaxies together, could it also have shaped the universe on even greater scales? Perhaps the graceful arrangement of galaxies across the heavens was not random after all, but the visible outline of an even larger invisible design that had been quietly guiding the cosmos since its earliest moments. As the idea of invisible matter slowly gained acceptance, astronomers found themselves standing before an entirely new mystery. Discovering that galaxies contained far more matter than they could see was astonishing enough. But another question soon followed, almost like the quiet echo of the first. If this unseen matter surrounds every galaxy, what role has it been playing throughout the history of the universe? The answer, it turned out, was far more profound than anyone had expected. Imagine waking before sunrise and walking through a meadow, covered in morning dew. At first, all you notice are countless tiny droplets sparkling in the first rays of light. They appear almost magical, scattered randomly across the field. But as you kneel closer, you begin to notice that the droplets are not floating freely at all. They are carefully tracing delicate strands of spider silk that were nearly invisible only moments before. The dew is not creating the web, it is simply revealing something that was already there. Astronomers began to realize that galaxies may be doing something very similar. The brilliant stars, glowing clouds of gas, and colourful nebulae that fill our telescopes are like the tiny drops of morning dew. Beautiful as they are, they may simply be outlining a much larger invisible structure stretching across the universe. This hidden framework has become known as the cosmic web. The name sounds almost poetic, yet it describes one of the most important discoveries in modern cosmology. When scientists use powerful computer simulations to recreate the evolution of the universe, something remarkable happens. If they include only the ordinary matter that makes up stars, planets, oceans, mountains, and people, the simulated universe struggles to produce the vast network of galaxies we actually observe. But when invisible dark matter is added, everything changes. Slowly, almost gracefully, enormous strands begin to emerge. These strands connect immense regions where galaxies gather together, while between them lie vast expanses that contain surprisingly little matter at all. The universe begins to resemble a giant web, with glowing galaxies decorating invisible threads that stretch across unimaginable distances. You might picture rivers flowing across a landscape. Water naturally follows valleys that already exist. The rivers do not carve every feature from the very beginning. Instead, they often reveal the shape of the land beneath them. In much the same way, ordinary matter appears to have flowed into valleys created by dark matter long before the first stars ever began to shine. This idea completely changed how astronomers understood the birth of galaxies. In the earliest moments after the Big Bang, the universe was astonishingly hot and remarkably smooth. Tiny differences in density existed, but they were incredibly small, almost like gentle ripples spreading across the surface of a perfectly calm lake. Over hundreds of millions of years, gravity quietly amplified those tiny differences. Where slightly more dark matter happened to gather, its gravity became just a little stronger. That stronger gravity attracted even more matter. As more matter accumulated, gravity became stronger still. The process continued patiently, almost unnoticed over immense stretches of time. Eventually, these invisible concentrations became enormous structures often described as dark matter halos. Although the word halo may bring to mind a glowing ring of light, these halos are neither bright nor visible. They are better imagined as vast regions where invisible matter has quietly gathered, creating deep gravitational valleys. Into those valleys flowed ordinary matter. Clouds of hydrogen and helium drifted inward. The gas became denser, gravity compressed it further, temperatures slowly rose. Then, at last, the first stars ignited. Those first stars were unlike anything we see today. They were enormous, brilliant, and short-lived. Inside their blazing cores they forged the first heavy elements: carbon, oxygen, iron, and many of the ingredients that would one day become planets, oceans, trees, and living creatures. When those giant stars reached the end of their lives, they scattered their newly created elements across the young universe. Future generations of stars inherited those materials. Around some of those younger stars, planets formed. On at least one small rocky world orbiting an ordinary yellow star, chemistry eventually became biology, and billions of years later, living beings began asking where they had come from. It is an astonishing chain of events. Invisible matter gathered first, galaxies followed, stars were born, heavy elements formed, planets appeared, life emerged. In that sense, dark matter is not simply another mysterious ingredient in the universe. It is one of the quiet architects of everything familiar. Without it, galaxies might never have formed in the way they did. Without galaxies, there would have been far fewer stars. Without generations of stars creating heavy elements, there would be no rocky planets, no oceans, and no people gazing upward in wonder. It is remarkable to think that something we have never directly seen may have helped make our own existence possible. Modern cosmologists often describe the universe as being made from three broad ingredients. Only a small portion consists of the ordinary matter that forms everything we can touch, see, and experience in daily life. A much larger portion consists of dark matter, whose gravity quietly shapes the architecture of the cosmos. And the largest portion of all appears to be something even stranger, a mysterious form of energy that influences the expansion of the universe itself. For now, however, our attention remains on the invisible framework that allowed galaxies to grow. As telescopes became more powerful, astronomers found increasing evidence for this enormous cosmic network. Clusters of galaxies appeared connected by immense filaments stretching across hundreds of millions of light years, while between them lay gigantic cosmic voids, regions so empty that they seemed almost unimaginable. From a great distance, the universe no longer resembled scattered islands of light. Instead, it looked almost alive, like the branching veins of a leaf, the delicate threads of frost spreading across a winter window, or the intricate roots of an ancient forest hidden beneath the soil. Nature, it seemed, enjoyed repeating beautiful patterns across vastly different scales. The more astronomers studied this invisible architecture, the clearer it became that dark matter was not simply solving an old puzzle about spinning galaxies. It was revealing an entirely new picture of reality. The stars we admire on clear nights are only the visible lights decorating a far greater structure, one that silently supports the universe much as unseen foundations support a great cathedral. And while scientists were becoming increasingly confident that this hidden framework existed, another challenge remained. Knowing that something shapes the universe is not quite the same as knowing what it is. Somewhere beneath mountains, inside carefully shielded laboratories, researchers were preparing delicate experiments in the hope that, for the very first time, humanity might catch a direct glimpse of the invisible substance that had quietly built the cosmos. By now, the evidence had become difficult to ignore. Galaxies rotated too quickly to be held together by the stars we could see. Enormous cosmic structures appeared to have formed around invisible foundations. Computer simulations repeatedly pointed toward the same conclusion. Something unseen was shaping the universe on the largest scales imaginable. Yet there remained one deeply human question: could we ever find it? Knowing that something exists because of its effects is very different from holding direct evidence in your hands. Long before astronomers discovered planets around distant stars, they first noticed tiny wobbles in the motion of their parent stars. Long before anyone photographed a black hole, scientists watched stars orbit an invisible object at the centre of our galaxy. Dark matter seemed to belong to that same tradition. It revealed itself through gravity, but never through light. And so began one of the most patient scientific searches in history. Imagine standing inside a vast forest just after a fresh snowfall. You never see the animal itself, but every morning you discover new footprints crossing the white landscape. Day after day, the tracks appear. They turn around trees, disappear behind rocks, and continue over distant hills. Eventually you become completely certain that the animal exists, even though it always remains hidden. Dark matter is rather like that mysterious traveller. Its footprints are everywhere. Its presence is unmistakable, but the traveller itself remains unseen. To search for something so elusive, scientists had to think differently. Ordinary telescopes would not help, because dark matter appears to interact very little with light. Looking harder through a telescope is a little like trying to hear the sound of a bird by staring more carefully at the sky. The tool simply is not designed for the task. Instead, researchers built extraordinarily sensitive experiments designed to wait patiently for an incredibly rare event. One of the most remarkable of these experiments lies deep beneath the Black Hills of South Dakota in the United States, inside the Sanford Underground Research Facility. It occupies tunnels that were once part of an old gold mine, reaching about a mile beneath the Earth's surface. At first, this might seem like an unusual place to search for the secrets of the universe. Why travel underground when the mysteries lie among the stars? The answer begins with another invisible visitor. Every second of every day, tiny high-energy particles from space constantly rain down upon our planet. These particles, known as cosmic rays, are completely natural. Earth's atmosphere blocks many of them, but countless others still reach the ground. For most of us, they pass unnoticed. But for an experiment trying to detect an extraordinarily rare interaction, they become unwanted noise. Imagine trying to hear the soft flutter of a butterfly's wings while standing beside a roaring waterfall. The butterfly may be there, but the surrounding noise overwhelms everything. Moving deep underground is like stepping into a quiet cave where the roar fades into silence. The thick layers of rock overhead act as a natural shield, blocking most of the cosmic rays and creating one of the quietest scientific environments on Earth. Silence, in this case, becomes a scientific instrument. Inside that underground laboratory stands one of the world's most sensitive dark matter experiments, called the Lux Zeppelin experiment. At its heart rests a large chamber filled with several tons of ultra-pure liquid xenon. Xenon is a rare gas that becomes a clear liquid when cooled to extremely low temperatures. Scientists chose it because its atoms are excellent at revealing tiny disturbances. The experiment is beautifully simple in its idea, even if the engineering behind it is astonishingly complex. If a dark matter particle were to pass through the detector, there is a very small chance that it might gently collide with the nucleus of a xenon atom. The collision would be incredibly subtle. Yet even such a tiny interaction could produce a faint flash of light, followed by a second signal created as tiny electric charges drift upward through the liquid. Sensitive instruments surrounding the chamber continuously watch for these delicate flashes. They wait, quietly, patiently, sometimes for months, sometimes for years. This may sound almost unbelievable, but much of modern experimental physics is an exercise in extraordinary patience. Researchers are often willing to wait years for a single event that could transform our understanding of reality. Among the earliest leading candidates for dark matter were hypothetical particles known as weakly interacting massive particles. Their name sounds complicated, but the basic idea is surprisingly gentle. These particles, if they exist, would possess mass, allowing gravity to feel their presence. while interacting so rarely with ordinary matter that billions of them could pass through your body every second without leaving the slightest trace. Another possibility is an entirely different particle called the axion, an incredibly light particle proposed to solve a separate puzzle in particle physics before scientists realised it might also explain dark matter. Still, another idea suggests that some dark matter could consist of tiny primordial black holes formed during the earliest moments of the universe, long before the first stars appeared. In recent years, scientists have become even more open-minded. Perhaps dark matter is not just one kind of particle. Perhaps it is an entire hidden family of particles, sometimes called the dark sector, interacting with one another in ways we have only begun to imagine. The possibilities continue to expand because nature has not yet revealed the answer. Curiously, one of the most important lessons from these experiments is that failure does not always mean failure. The Lux Zeppelin experiment has not yet announced the direct discovery of dark matter. Neither have several other remarkable experiments around the world, yet every careful observation still teaches us something valuable. Each result allows scientists to eliminate possibilities. Imagine searching for a lost key inside a large house. Every room you carefully examine and rule out narrows the search. You may not have found the key today, but you now know with certainty where it is not. The mystery grows smaller, even if the answer has not yet appeared. Science often advances in exactly this quiet, methodical way. Every unsuccessful search refines the next search. Every unanswered question points more clearly toward the questions worth asking. It is a process built not upon dramatic certainty, but upon steady curiosity. And while physicists continued listening for the faintest whisper from dark matter beneath mountains of ancient rock, another mystery was quietly unfolding across the universe itself. This one would not be hidden inside galaxies. It would be written into the expansion of space itself, gently reshaping the destiny of every galaxy, every star, and every future night sky. While physicists patiently searched for the invisible matter that seemed to hold galaxies together, another mystery was quietly waiting to be discovered. Unlike dark matter, this new puzzle would not reveal itself inside a detector buried beneath mountains, nor would it hide within the graceful rotation of galaxies. Instead, it would emerge from something much larger, the universe itself. To understand how astonishing this discovery would become, it helps to step back and look at the long journey that brought humanity to this moment. For most of human history, people believed the heavens were permanent. The stars seemed fixed. The constellations appeared unchanged. The planets wandered slowly across the sky, but the universe itself felt eternal, almost like a magnificent painting hanging above the Earth. Centuries passed before that picture began to change. Nicholas Copernicus suggested that Earth was not the centre of everything. Instead, our planet travelled around the Sun. It was a simple idea, yet it quietly shifted humanity's place in the cosmos. Later came Isaac Newton, who revealed that the same force causing an apple to fall also guided the moon around Earth and the planets around the Sun. Suddenly, the heavens and the Earth were no longer separate worlds governed by different rules. They belonged to the same elegant universe. Then, in the early 20th century, Albert Einstein carried this understanding even further. Rather than imagining gravity as an invisible force pulling objects together across empty space, Einstein proposed something far more beautiful. Imagine placing a heavy stone onto the surface of a soft blanket. The blanket bends beneath the stone. Now imagine rolling a small marble nearby. The marble curves toward the larger object, not because the stone is reaching out to pull it, but because the blanket itself has changed shape. Einstein suggested that space and time behave in a similar way. Mass and energy gently curve the fabric of space and time, and everything else simply follows those curves. It was one of the most profound ideas ever developed in science. Yet Einstein himself believed the universe as a whole was unchanging. There was one problem. Gravity is always attractive. If the universe contained countless stars and galaxies pulling on one another, then over immense periods of time everything should slowly collapse inward. Einstein found this unsettling because astronomers of his day believed the universe was static. To preserve that picture, he introduced an additional idea into his equations, a gentle outward influence that perfectly balanced gravity, allowing the universe to remain unchanged. Years later, this idea became known as the cosmological constant. At the time, however, it seemed little more than a mathematical adjustment. Then came Edwin Hubble. Using observations from the Mount Wilson Observatory in California, Hubble studied distant galaxies and noticed something extraordinary. Almost every galaxy appeared to be moving away from us. Even more surprising, the farther away a galaxy was, the faster it seemed to recede. At first glance, this might sound as though Earth occupies a special place at the centre of everything. But that is not what the observations mean. Imagine raisins scattered throughout a loaf of bread before it begins to bake. As the dough rises in the oven, every raisin moves away from every other raisin. No single raisin sits at the centre of the expansion. The bread itself is growing. The universe behaves in much the same way. Space itself expands. Galaxies are not simply flying through space. Instead, the distances between galaxies gradually increase because the very fabric of the universe stretches over time. This discovery completely transformed cosmology. If the universe is expanding today, then long ago everything must have been much closer together. Following that idea backward eventually leads to what we now call the Big Bang, a time when the observable universe was unimaginably hot, dense, and young. The Big Bang was not an explosion into empty space. Rather, it marked the beginning of the expansion of space itself. Decades later, astronomers discovered another remarkable clue supporting this picture. Throughout the entire sky, they detected an extremely faint glow, a gentle whisper of ancient light that has been travelling through the universe for almost its entire history. This ancient glow is known as the cosmic microwave background. You can think of it as the universe's oldest surviving photograph, preserving a moment when the cosmos was only a few 100,000 years old. Tiny variations within this ancient light would eventually help scientists understand how galaxies first began to form. By the 1970s, the expanding universe and the Big Bang had become widely accepted. Most astronomers believed they understood what would happen next. Gravity, they reasoned, should slowly pull everything back together. The expansion might continue forever, but it should gradually become slower with time. It was a sensible prediction. After all, if you throw a ball into the air, gravity steadily reduces its speed before it eventually falls back down. Surely the universe would behave in a similar way. To answer this question, astronomers needed an extraordinarily reliable way to measure immense cosmic distances. Fortunately, nature had already provided one. Certain exploding stars, known as Type I supernovas, shine with remarkably consistent brightness. Because astronomers know approximately how bright these explosions truly are, they can compare that intrinsic brightness with how bright they appear from Earth. The difference reveals their distance, much as a distant lighthouse appears dimmer than one nearby. Throughout the 1990s, two international teams searched tirelessly for these distant stellar explosions. Night after night, they compared observations, checked calculations, and questioned every surprising result. At first, the numbers seemed almost impossible. The distant supernovas appeared dimmer than expected. That could mean only one extraordinary thing. The universe had expanded more than anyone predicted. After months of careful analysis, both research teams reached the same astonishing conclusion. The expansion of the universe was not slowing down. It was speeding up. The discovery sent shockwaves through cosmology. Some unknown influence was overcoming gravity across the largest scales imaginable. It was as though the loaf of rising bread had quietly begun expanding faster and faster, even though no baker had turned up the oven. Astronomers gave this mysterious phenomenon a simple name: dark energy. The name does not explain what it is. It merely acknowledges that something unknown appears to be driving the accelerated expansion of the universe. In a surprising twist of history, Einstein's abandoned cosmological constant suddenly became relevant once again. The idea he had introduced to preserve a static universe now seemed remarkably similar to the mysterious influence accelerating the expanding one. Whether dark energy truly is Einstein's cosmological constant, or something even stranger, remains one of the greatest unanswered questions in modern science. The universe once again had surprised us. Just as we began to understand the invisible matter holding galaxies together, we discovered another invisible influence gently pulling the entire cosmos toward an uncertain future. The discovery of dark energy answered one question, but almost immediately replaced it with another that was even more mysterious. If something is causing the universe to expand faster and faster, what exactly is it? The honest answer is surprisingly simple. No one knows. That uncertainty may sound frustrating at first, but it is also one of the reasons modern cosmology is such an exciting field. Scientists have measured the effects of dark energy with increasing confidence, yet its true nature remains hidden. It is a little like standing on a quiet beach, watching the tide slowly rise. You may not see the distant storm or understand every movement of the ocean, but the water at your feet leaves no doubt that something powerful is taking place far beyond the horizon. Dark energy announces itself in much the same quiet way. We cannot point a telescope toward it and take a photograph. We cannot collect it inside a laboratory. We cannot hold it in our hands. Instead, we see its influence written across the expanding universe. One of the most remarkable aspects of this story is that dark energy has not always been the dominant influence shaping the cosmos. If we could travel backward through time, billions of years into the past, we would find a very different universe. Galaxies were much closer together. Gravity had a stronger grip on the large-scale structure of the cosmos. Every galaxy was pulling on its neighbours, slowing the overall expansion that had begun after the Big Bang. For billions of years, gravity appeared to be winning this quiet contest. But the universe itself was changing. As space continued expanding, galaxies drifted farther apart. Matter became more spread out, and the gravitational pull between distant galaxies gradually weakened. It was not because gravity itself had become weaker. Rather, the galaxies were simply becoming more isolated, like voices growing fainter as people slowly walk away from one another across an open field. Dark energy, however, behaved differently. Unlike matter, which becomes more diluted as space expands, dark energy appears to remain remarkably persistent. As the universe grew larger and larger, its influence became increasingly important. Astronomers estimate that roughly 6 billion years ago, a profound transition took place. For countless ages, gravity had acted as the dominant architect of cosmic evolution. Then, very gradually, dark energy began to take the lead. There was no sudden explosion, no dramatic cosmic event, no single moment when astronomers could point to the sky and say, "Everything changed today." Instead, it was more like the slow arrival of evening. You rarely notice the exact second when afternoon becomes dusk. The light simply softens little by little until, almost without realizing it, you find yourself beneath a sky filled with stars. The rise of dark energy unfolded with similar patience. Little by little, its influence became stronger than gravity on the larger scales of the universe. Today, many cosmologists describe our era as living in the age of dark energy. That phrase may sound dramatic, but it simply reflects the idea that the expansion of the universe is now increasingly governed by this mysterious component rather than by the combined gravity of galaxies alone. It is a curious thought. Everything around us feels stable. The Earth circles the Sun. The Moon circles the Earth. Our galaxy continues its slow rotation. Nothing in our daily lives suggests that the universe itself is expanding ever more rapidly. That is because dark energy works primarily across immense cosmic distances. Inside galaxies, gravity remains overwhelmingly stronger. The Milky Way will not suddenly fly apart because of dark energy. The solar system will continue its graceful dance for billions of years. Even our neighbouring Andromeda galaxy is still moving toward us under the influence of gravity, and the two galaxies are expected to merge in the distant future. Dark energy does not interrupt these local relationships. Its influence only becomes significant when we look across the enormous spaces separating distant groups of galaxies. Imagine standing on a hill at sunset, watching dozens of lanterns floating gently across a calm lake. Nearby lanterns remain close together, drifting almost side by side. Those much farther away seem to separate more quickly as the distance between them grows. The farther you look, the more noticeable the widening gaps become. The universe behaves in a surprisingly similar way. Entire clusters of galaxies continue drifting farther apart as space itself expands. If this process continues indefinitely, and current observations suggest that it may, the future universe will become a much lonelier place. This is one of the most quietly moving ideas in all of cosmology. Billions upon billions of years from now, many galaxies that are visible today will have drifted so far away that their light will never reach future observers. It is not because those galaxies have disappeared, nor because their stars have stopped shining. Rather, the space between us and them will have expanded so greatly that the light they emit can no longer cross the ever-growing distance. Imagine watching a small boat slowly sailing away across an endless ocean. For a long time, you can still make out its shape, then only its sail. Eventually it becomes nothing more than a tiny white dot against the horizon. Finally, it disappears from sight altogether. The boat has not vanished. It has simply travelled beyond what your eyes can follow. Dark energy may gradually produce a similar effect on the universe itself. Future civilizations, if any exist trillions of years from now, might see only their own local collection of galaxies. Everything beyond that could lie forever beyond observation. The night sky would become darker, quieter, more isolated. Some cosmologists describe this distant future as a cold and dilute universe. Stars will continue to shine for unimaginable lengths of time, but eventually even they will exhaust their fuel. New stars will become increasingly rare. Galaxies will grow dimmer. The universe will slowly settle into extraordinary stillness. It is sometimes called the heat death of the universe, although the phrase can sound much harsher than the reality it describes. Rather than imagining destruction, it may be gentler to picture a great concert slowly reaching its final notes. The musicians do not suddenly stop. One instrument becomes quiet, then another. The melody gradually fades until only silence remains. Whether this vision truly represents the ultimate future depends on a question we still cannot answer. Is dark energy constant, or has it changed over cosmic history? If its strength remains exactly the same forever, then the universe may continue expanding peacefully for unimaginable ages. But if dark energy slowly changes over time, entirely different futures could await the cosmos. This uncertainty reminds us of something wonderfully human. Even after decades of astonishing discoveries, we still stand at the edge of an unfinished story. The universe has revealed enough to inspire awe, yet it continues to protect some of its deepest secrets with remarkable patience. And as scientists searched for clues hidden within the expansion of space itself, another mystery quietly emerged from the very measurements that had made these discoveries possible. The more precisely astronomers measured the universe, the more they found that reality refused to fit together quite as neatly as anyone had expected. As the 20th century gave way to the 21st, astronomy entered a remarkable new era. For centuries, scientists had struggled simply to gather enough observations to understand the universe. Every new telescope brought another handful of clues. Every generation worked with instruments that seemed miraculous for their time. Now, however, the challenge was changing. The problem was no longer a lack of information. Instead, astronomers suddenly found themselves surrounded by an astonishing abundance of it. Powerful space telescopes observed distant galaxies with breathtaking clarity. Giant observatories on mountaintops collected light from the edge of the observable universe. Spacecraft mapped the ancient glow left behind by the Big Bang with extraordinary precision. Computers processed unimaginable quantities of information, uncovering patterns far too subtle for the human eye to notice. It felt as though humanity had finally begun reading the universe in high definition. Naturally, many scientists believed that the great puzzles of cosmology were finally approaching their solutions. Instead, the opposite happened. The more carefully we measured the universe, the more clearly one stubborn disagreement refused to disappear. It concerned a surprisingly simple question. How fast is the universe expanding today? At first, this might seem like something astronomers should be able to measure without difficulty. After all, Edwin Hubble had already shown that galaxies move farther apart as the universe expands. Decades of observations had refined those measurements again and again. Surely by now everyone should arrive at the same answer, yet they did not. Imagine several skilled bakers preparing the same recipe. They carefully measure every ingredient, use identical ovens, and follow the same instructions. When the bread is finished, however, one loaf consistently rises slightly higher than the others. At first, you might suspect a simple mistake. Someone must have measured incorrectly. Perhaps one thermometer is inaccurate. Perhaps one clock runs a little fast, so everyone checks their work. Again and again. Yet the small difference refuses to disappear. This is very similar to what astronomers began experiencing. One group measured the expansion of the universe by observing relatively nearby objects, whose distances could be determined step by step. They used special stars called Cepheid variable stars, whose gentle rhythm of brightening and dimming allows astronomers to calculate their true brightness. From there, they measured nearby galaxies, then more distant galaxies, gradually extending what is often called the cosmic distance ladder. It was a careful process, built one reliable step upon another. Another group approached the problem very differently. Instead of observing today's nearby universe, they studied the faint glow of the cosmic microwave background, the ancient light released when the universe was only a few 100,000 years old. This ancient light contains delicate patterns that reveal the conditions of the early universe with astonishing accuracy. By combining those observations with our best understanding of cosmology, scientists could predict how rapidly the universe should be expanding today. Both methods were elegant. Both relied upon decades of careful research. Both involved independent teams of highly experienced scientists. Yet their answers stubbornly refused to agree. The difference was not enormous, but it was persistent, and in science, a persistent disagreement is often far more interesting than a dramatic one. This puzzle became known as the Hubble Tension. The word tension does not suggest conflict between scientists. Rather, it describes the growing mismatch between two exceptionally careful measurements that both appear trustworthy. For years, researchers wondered whether hidden errors might explain the disagreement. Perhaps one telescope needed better calibration. Perhaps tiny sources of dust affected the observations. Perhaps some overlooked bias had quietly influenced the results. Scientists tested every possibility they could imagine. The measurements became better. The instruments became more accurate. Independent research groups repeated the work. Instead of disappearing, the tension remained. Imagine two beautifully crafted clocks hanging on opposite walls of the same room. Each keeps remarkably precise time. Each has been carefully tested. Yet one consistently gains a few seconds every day. Neither clock appears broken, but they cannot both be perfectly correct. Sooner or later, you begin wondering whether there is something about the room itself that neither clock fully explains. That possibility now excites many cosmologists. Perhaps the disagreement does not arise from faulty measurements at all. Perhaps it is quietly pointing toward new physics that has not yet been discovered. Some researchers wonder whether dark energy behaves slightly differently than current models assume. Others ask whether unknown particles may have existed in the young universe. Still others explore whether gravity itself behaves in unexpected ways across enormous cosmic distances. None of these ideas has yet solved the mystery, but each possibility reminds us that science advances most rapidly when reality refuses to match our expectations. History offers many examples. The strange motion of Mercury eventually helped inspire Einstein's theory of general relativity. Tiny irregularities in the orbit of Uranus led to the discovery of Neptune. Unexpected patterns in starlight revealed the expanding universe. Again and again, small inconsistencies have opened entirely new chapters in science. Perhaps the Hubble tension will do the same, or perhaps its explanation will prove surprisingly ordinary. Either outcome would deepen our understanding. One of the quiet beauties of science is that uncertainty is never something to fear. It is an invitation. An unanswered question does not represent failure. It marks the edge of knowledge, the place where discovery quietly waits. Today, astronomers continue refining these measurements with remarkable patience. New space telescopes, improved detectors, and increasingly sophisticated observations are helping reduce uncertainties year after year. Meanwhile, enormous computer simulations recreate billions of years of cosmic evolution, allowing scientists to compare theoretical universes with the one we actually observe. The agreement between theory and observation is extraordinary in many areas, yet this one small disagreement continues whispering that there may still be another secret hidden beneath the surface. It is rather comforting in a way. Even after half a century of astonishing progress, the universe has not become smaller or simpler. It remains wonderfully capable of surprising us. Every answer illuminates another doorway. Every discovery reveals another horizon. And now, with powerful new observatories preparing to scan the heavens more deeply than ever before, humanity stands ready for another chapter in this remarkable story, one that may reshape our understanding of the cosmos all over again. Every generation of astronomers inherits two remarkable gifts from those who came before. The first is knowledge. The second is a new collection of unanswered questions. That may sound like an unusual kind of progress, but it is one of the defining features of science. Every discovery expands our understanding, yet it also reveals how much more remains hidden. 50 years ago, astronomers wondered whether galaxies contained unseen matter. Today, they ask what that matter actually is. They wondered whether the expansion of the universe would slow down. Today, they ask why it is accelerating. The questions have changed, but the spirit of curiosity remains wonderfully familiar. To answer these new questions, humanity is building instruments unlike anything that has existed before. Imagine trying to understand an enormous forest by looking through a tiny window. You might see a few trees, a patch of sunlight, perhaps the movement of a bird. Every new window gives you another small glimpse, but you never quite understand the forest as a whole. Now imagine climbing above the trees in a quiet balloon at sunrise. Suddenly, rivers, valleys, hills, and winding paths all become visible together. That is what each new generation of observatories hopes to accomplish. Rather than collecting only isolated pieces of information, they aim to reveal the larger patterns that connect everything. One of the most anticipated of these observatories is the Vera C. Rubin Observatory, named in honor of the astronomer whose careful work transformed our understanding of the invisible universe. There is something quietly fitting about this tribute. Rubin spent years patiently measuring the motions of distant stars, revealing evidence for dark matter through extraordinary attention to detail. Now, an observatory carrying her name will continue that tradition on an even grander scale. Unlike many telescopes that focus on small portions of the sky, the Rubin Observatory has been designed to survey almost the entire visible southern sky again and again over many years. Every few nights, it will create a fresh portrait of the heavens, night after night, year after year. This repeated survey will allow astronomers to notice subtle changes that would otherwise remain invisible. New supernovas will appear. Asteroids will quietly move against the background stars. Variable stars will brighten and fade. Entire galaxies may reveal tiny changes that help refine our understanding of cosmic expansion. The observatory is expected to generate an extraordinary amount of information, far more than any individual scientist could possibly examine alone. This has led astronomy into another new partnership: artificial intelligence. Modern computer systems are becoming invaluable assistants, helping researchers identify unusual objects, detect faint patterns, and sort through enormous collections of observations. It is important to remember that these systems are not replacing scientists. Rather, they act much like careful librarians inside an unimaginably vast library, quickly finding books that deserve closer human attention. Curiosity still belongs to people. The computers simply help us navigate the overwhelming abundance of information. Meanwhile, high above Earth's atmosphere, another remarkable observatory has already begun transforming astronomy. The James Webb Space Telescope peers deeper into space than any previous space telescope designed primarily for infrared light. Looking deeper into space also means looking farther back in time. Because light requires time to travel, observing extremely distant galaxies allows astronomers to see them as they existed billions of years ago. It is rather like opening an old family photograph album. Each page reveals an earlier moment in someone's life. Together, those photographs tell a story stretching across many decades. The James Webb Space Telescope performs something similar on a cosmic scale. Its observations allow astronomers to study galaxies when the universe itself was still remarkably young. Some of its discoveries have already surprised researchers. Galaxies have appeared brighter, larger, and more developed than many scientists expected so early in cosmic history. These observations do not necessarily overturn everything we know about cosmology. Instead, they encourage scientists to refine existing models and ask even better questions. Once again, the universe reminds us that it is often more creative than our expectations. Another exciting frontier comes from an entirely different way of exploring the cosmos. For centuries, astronomy depended almost entirely upon light: visible light, radio waves, infrared light, ultraviolet light, X-rays, gamma rays. Each revealed different aspects of the universe. Then humanity learned to observe something entirely new: gravitational waves. These are tiny ripples travelling through the fabric of space and time itself, created when extraordinarily massive objects such as black holes or neutron stars collide. The first direct detection of gravitational waves marked the beginning of what many scientists call multi-messenger astronomy. Rather than studying the universe using only light, astronomers can now combine information carried by light, gravitational waves, and other cosmic messengers to build a far richer picture of distant events. Imagine attending a beautiful symphony while wearing earplugs. You might still see the musicians moving. You could watch the conductor. You would understand that something extraordinary is happening, but only after removing the earplugs would you experience the full richness of the performance. Gravitational waves have given astronomy another sense with which to experience the universe. The story becomes fuller, more complete, and perhaps even more beautiful. Future observatories promise to extend this transformation even further. Some will search for faint gravitational waves left over from the earliest moments after the Big Bang. Others will map the distribution of galaxies with unprecedented precision. Still others will search for clues about dark matter, dark energy, and the invisible structures connecting the cosmos. Every new instrument represents another conversation between humanity and the universe. We ask a question. The universe answers. Sometimes the answer is exactly what we expected. More often, it quietly surprises us. That pattern has repeated itself throughout the history of cosmology. The greatest discoveries have rarely arrived because scientists proved themselves right. They arrived because nature revealed something even more interesting than anyone had imagined. As remarkable as our technology has become, perhaps our greatest scientific instrument remains something much older: wonder. Every telescope, every spacecraft, every detector, and every computer ultimately begins with a simple decision made by curious minds: to keep asking, to keep observing, to remain willing to change our understanding when the evidence leads somewhere unexpected. It is that quiet willingness to learn that has transformed our picture of the universe over the past 50 years, and it may soon carry us toward discoveries that today still exist only as faint possibilities, waiting patiently beyond the edge of what we currently know. As our journey through the last 50 years of cosmology gently draws toward its close, it becomes clear that the greatest transformation has not been in the universe itself. The stars have continued to shine, galaxies have continued their slow dance across unimaginable distances. The ancient light from the Big Bang has continued travelling through space, just as it has for billions of years. The universe has remained wonderfully patient. It is we who have changed. Half a century ago, many astronomers believed they were beginning to understand the broad outline of the cosmos. There were certainly unanswered questions, but there was also a quiet confidence that the biggest pieces of the puzzle were falling into place. Instead, every major discovery opened another door. When we learned that galaxies rotated too quickly, we discovered dark matter. When we measured the expansion of the universe more carefully, we encountered dark energy. When our telescopes became more precise, new tensions appeared in our measurements. When we learned to detect gravitational waves, the universe began speaking in an entirely new language. Again and again, certainty gave way to curiosity. That pattern may be one of the most beautiful characteristics of science. Imagine walking through a peaceful forest at dawn. The rising sunlight allows you to see farther than before. At first, you feel as though the path ahead has finally become clear, but as the light grows brighter, you notice countless smaller trails branching away into the trees. The better you can see, the more possibilities appear. Knowledge often behaves in exactly the same way. Each answer illuminates new questions that were previously invisible. One of the greatest mysteries still facing cosmologists concerns the true nature of dark matter. After decades of searching, we know an extraordinary amount about what it does. It shapes galaxies, it guides the growth of the cosmic web, it bends light through gravity, it helped build the large-scale architecture of the universe. Yet we still do not know what it actually is. Is it made of particles unlike anything yet discovered? Is it composed of several different ingredients working together? Or is the universe quietly pointing toward an even deeper understanding of gravity itself? No one yet knows. Dark energy remains equally mysterious. We observe its influence with increasing confidence, yet its identity remains hidden. Is it truly the cosmological constant that Albert Einstein once introduced into his equations? Is it a property of empty space itself? Or is it something that slowly changes as the universe evolves? Each possibility would tell a profoundly different story about the fate of the cosmos. Even the earliest moments of the universe remain wrapped in mystery. Astronomers have reconstructed an astonishingly detailed picture of cosmic history, stretching back almost to the beginning. They understand how the first atoms formed, they understand how stars ignited, they understand how galaxies gradually assembled across billions of years. Yet the first tiny fraction of a second after the Big Bang remains one of the greatest frontiers in all of science. Our current theories describe the era only incompletely. Gravity, which governs galaxies so beautifully, refuses to fit comfortably alongside quantum physics, which governs the smallest particles of nature. Somewhere beyond our current understanding lies a deeper framework that may unite these two remarkable descriptions of reality. Scientists continue searching for it with extraordinary patience. Perhaps future generations will discover it. Perhaps they will not. Either possibility reminds us that knowledge is not guaranteed. It is earned slowly, observation by observation, question by question. History suggests something else worth remembering. Many of the discoveries we now consider foundational were once regarded as unlikely, even impossible. There was a time when no one knew that galaxies existed beyond the Milky Way. There was a time when black holes seemed like mathematical curiosities. There was a time when planets around other stars belonged almost entirely to imagination. There was a time when dark matter and dark energy had not yet entered the scientific vocabulary. Each generation inherits mysteries that appear permanent. Then quietly, one careful observation changes everything. That is why many astronomers speak with remarkable humility. They know that today's standard picture of the universe is extraordinarily successful. It explains an immense range of observations with beautiful consistency. Yet they also know that every scientific model is ultimately an approximation of reality. Nature is always free to surprise us. Perhaps the next great revolution has already begun, hidden within measurements that seem only slightly unusual today. Perhaps the Hubble Tension is quietly pointing toward new physics. Perhaps an unexpected signal buried inside future observations will reveal the identity of dark matter. Perhaps entirely new questions we have not yet imagined, are waiting for future scientists to ask. That possibility is deeply comforting. It reminds us that the adventure of discovery is far from over. There will always be another horizon, another mystery, another quiet invitation to look upward with fresh eyes. And perhaps that has been the greatest lesson of the past 50 years. Science is not a journey toward absolute certainty. It is a lifelong conversation with the universe. Sometimes the universe answers clearly, sometimes it answers with silence, sometimes it responds by asking an even better question. As you rest beneath tonight's sky, it is worth remembering that every star you see belongs to a story still being written. The light arriving at your eyes has travelled extraordinary distances. Some began its journey before human civilization existed. Some left its stars before our own sun was born. Across those immense stretches of space and time, the universe has carried its quiet messages with endless patience. We've only recently learned how to listen. Perhaps somewhere beyond the reach of today's telescopes, new discoveries are already waiting. Invisible structures, unknown particles, unexpected laws of nature, or ideas so unfamiliar that we do not yet possess the words to describe them. The universe has surprised humanity many times before. There is every reason to believe it will do so again. And so, as tonight's exploration gently comes to an end, you may find yourself looking at the night sky a little differently. The stars above have not changed during these past few moments, yet perhaps they feel a little deeper, a little more mysterious, and a little more welcoming than before. They remind us that the universe is not simply a collection of distant objects, but an endless invitation to wonder. As you relax and allow your thoughts to grow quieter, you can leave these questions exactly where they belong, resting peacefully among the stars. There is no need to solve them tonight. Generations of curious minds have spent lifetimes exploring them, and many answers are still patiently waiting in the darkness. For now, it is enough simply to appreciate the extraordinary journey that has brought humanity from a small planet around an ordinary star to a place where we can begin to glimpse the hidden architecture of the cosmos. May that sense of quiet wonder stay with you as the night grows still, and may the vast, gentle universe above remind you that there is beauty not only in the answers we discover, but also in the mysteries that continue to inspire us. Rest well, and good night.